Hey guys, welcome to Unit 8, Notes B. In Notes B, we're going to talk about concentration and all the different ways that we can express it. So what is concentration? What are we trying to describe? Concentration basically tells you how much solute is in a solution, how much particle is concentrated together inside of the solution. So it is similar to solubility. When we looked at solubility in Notes A, we looked at how much solute a solution could hold. What is the maximum amount in order to make it saturated? Concentration is similar in that it's kind of describing how much solute is in solution, but solubility is a unique concentration that makes the solution saturated. Concentration could describe saturated or unsaturated or supersaturated solutions. So concentration is basically more broad. It's describing any amount of solute in any amount of solution. So there's several different ways that we can express this. Lots of ways to quantify how much solute is present. The first one we're going to look at is called mass percent. Now we've done mass percent before when we looked at the mass of an atom in an entire compound and how much that atom contributed to the mass of the entire compound. So you may remember we took the part that we were interested in and divided it by the whole mass of the compound. This is going to be very similar when we look at solutions. I'm going to be interested in the mass of the solute, how much solute is present, and comparing that to the mass of the total solution. So solution, you may remember, it includes two components, not only the solute, but also the solvent. So we're going to need to combine the solute and solvent mass in order to get our total mass of the solution. Put the mass of the solute on top, you divide, you multiply by 100, you got your mass percent. So let's try a problem. What is the percentage of the sodium chloride in a solution if we dissolve 24 grams of NaCl in 152 grams of the water? So to get my mass percent, on top I'm going to put mass of the solute, and on bottom I'll put mass of the solution. Mass solution. So the solute would be what's being dissolved, 24 grams of the sodium chloride. The salt is our solute in salt water. So on top, we'll put 24 grams. On bottom, I want the mass of the total solution. So is 152 grams of water the same as the mass of the total solution? Well, no, that would only be the mass of the solvent. We want the 152 grams of the solvent plus the 24 grams of the solute. That together will make the mass of the solution. So if I find 24 grams relative to that as a percentage, I will have my mass percent of solute. So let's get that in the calculator. So when you add the 152 and the 24, you get 176 total grams of the solvent, which is about 14% sodium chloride in the solution. The next way we can quantify concentration is something called molality. So let me warn you up front. In this unit, we will have both molarity and molality. See how similar those two things sound? And both of them have a variable of m. The difference is with molality, it's a lowercase m, spelled with two L's. Molarity will be a capital M spelled with an L and an R. So you want to be really careful which one they're giving you. For molality, it has to be the moles of solute. They may give you gram that you have to convert. And then divided by the kilograms of solvent. Again, they may give you gram that you have to convert. So you would use your mole conversion on the top and dimensional analysis to convert your units on the bottom. The idea with all of these calculations is to get the exact units specified by the formula, plug them in, and then you can solve for the type of concentration we're looking for. So let's try one. We're looking for molality, and so that means I'm going to be using the formula where molality is moles of the solute per kilogram of the solvent. It gives me the mass of a sugar and the mass of a water. So the first thing that you want to decide is which one's the solute and which one's the solvent. Water is our universal solvent, and sugar is what's being dissolved by the water, so that would be our solute. So for the solute, we're going to take our 12.8 grams, and we need to convert it into moles. So gram will go on the bottom and mole on top. And 1 mole of regular sugar is equal to about 180 grams molar mass of regular sugar. So this is going to give us our moles that we can then plug into the top. Then we're going to need to convert our solvent. So the solvent is given as 187.5 grams. So we can convert gram to kilogram using dimensional analysis. Gram on the bottom, kilogram on top, and 1 kilogram is equal to 1,000 grams. Or you may know the trick where you're moving the decimal place back 3 places. So this is going to be 0.1875 kilograms, which I can then plug in on the bottom. So we get our moles on top and the kilograms on bottom, and then we'll be able to solve for molality. So let's go ahead and see what our math works out to. So when you take the 12.8 and divide it by the 180, you get 0.0711 moles. When you divide that by our kilograms, not our grams, but our kilograms, we're going to find our molality. So for this example, that would be 0.379 molality. You just have to convert to the proper units, plug into the formula. Let's look at one more. How many grams of water must be used to dissolve 50 grams of sugar? So here's a mass it's giving me, and I know I have water, which would be the solvent. So that would make this different type of sugar our solute. So first thing we want to figure out, what's the solute, what's the solvent? So it actually tells me the molality this time, and I'm looking for the amount of water, the grams of water. So the molality is given of 1.25, and the sugar, it would be a mass of solute given to be 50 grams. So if I try to use my molality equation, I'm going to have different pieces of information given this time. On top, I would always have mole solute, and on bottom, kilogram solvent. So what do I have that can actually go into that formula? My molality should plug right in. I can plug in the 1.25. On the left, do I have moles of solute or kilograms of solvent? Well, not yet, but I do have the mass of solute. So solute, I can see, needs to be converted to moles. So I'm going to start with my 50 grams and do a mole conversion. Gram on the bottom, mole on top, always 1 mole. And here we'll plug in the molar mass of this sucrose, or this bigger sugar molecule. That's going to give me the moles that I can then plug in on the top. And then what I wouldn't know is the kilograms on the bottom. It will automatically be in kilograms because we're using molality. It is by definition going to give you kilograms, which we're then going to have to use dimensional analysis to get it into grams. So the molar mass of this big molecule is 342 grams. And so that would convert to 0.1462 moles. So that's what I'm going to be able to plug in on top with the given molality to solve for the bottom, the x on the bottom. Careful with your algebra here. In order to get x out of the denominator, you would multiply both sides by x. And then essentially to isolate over here, we would divide both sides by 1.25 in order to isolate x. And again, the catch is when you solve for x, you automatically get kilograms. So then we would be multiplying by 1,000 in order to get that into grams for 117 grams of water. So using the molality equation allows us to solve for specific information about solute and solvent. All right. Next type of concentration that we're going to look at is something called normality. So normality is actually a spin-off of something called molarity. Not the molality that we just talked about, but actually something called molarity, which I'm saving for the end because it's the actual special SI unit. So they're going to give you a set molarity and ask you to find the normality. What you have to do is multiply that molarity by the number of cation charges. Basically, that really should say positive oxidation number, but since we haven't covered oxidation numbers yet, I want to simplify that and just tell you I'm looking for the charges on the cation for an example like this. So, if I have H2SO4, for example, I know that the hydrogen has a +1 charge. The catch is there are 2 of those. So that would be a total of +2. So I'm just going to take that +2 and multiply by the given molarity, 3.0. And that's going to convert molarity into normality. So 2 times 3 is, of course, 6. This being an exact number, I'll keep my 6.0, but now the units would be a capital N instead of that capital M. So this is going to convert molarity into normality. Notice that I didn't give you a balanced equation when I asked you to do this conversion. That kind of insinuates that coefficients won't matter. All that matter are the subscripts on the cation. You find the charge of the cation and you multiply that by any subscripts that you have on the cation. That's going to be your total positive charges. Then you're going to multiply that by the given molarity in order to find normality. All right, we're going to take a quick break here so I can get set up to show you all about molarity. We're going to learn how to use that to make some standard solutions. See you in a minute. Hey guys, let's dig into molarity now, the most important unit that we're going to learn for concentrations. So molarity has the R instead of the L. It does look similar to molality, but molarity has the R. The symbol is also a capital M as opposed to the lowercase m for molality. It still has moles on top, but now we're going to have liters of solution on the bottom. This is the most important, I say, because this is typically how when you purchase chemicals, when you want to know how to label chemicals for storage, you're going to label them by their molarity. So if we have 4M hydrochloric acid, that would be a 4 molar hydrochloric acid, or 4 moles of hydrochloric acid particles in an entire liter of solution. So concentration is still referring to the basic amount of solute in solution, but the preferred units are molarity. There's also some shorthand I wanted to point out real quick. If you ever see a chemical formula with square brackets around them, that means we're looking for the concentration. You're going to see this in some of our future units. When you express concentration for things that are in brackets, you would always want to use molarity. So this would read as the concentration of hydrochloric acid is equal to 4 molar. All right, let's try an example where we actually solve for the molarity. So what's given here is the 58 grams of NaCl, which we know is our solute, dissolved in 1 liter of total solution. So it's already giving it to us as per liter of solution, which is nice. So let's deal with the issue of the solute. The formula says for the solute, we need to convert to moles, but we are given grams. So this is going to be your basic mole conversion. 58 grams over 1, putting gram on the bottom and mole on top, 1 mole to the molar mass of NaCl, which is 58.44. So 58 divided by basically 58 is about 1. Actually, this works out to be 0.99 with 2 sig figs. And the unit would be capital M for molarity. So we found our molarity, or actually, sorry, that was just moles so far. Getting ahead of myself here. But now to find the molarity, we're just going to divide by 1, which is why I got ahead of myself there. So we got 0.99 moles divided by that 1 liter of solution. And that's going to now give you the 0.99. And when you have mole per liter, by definition, that is molarity. So our final answer should have the units of capital M when you solve for molarity. There we go. So just like with some of our other types of concentrations, the main thing is to be careful of your units. You want to make sure that you convert grams into moles for the solute. And say they did give you milliliters or some other number of liters, you want to make sure that you've got it in liters of solution when you divide by liters in the bottom. And that'll give you molarity. This is really useful for creating solutions. Typically, when you make a solution, you want to make sure that you know the concentration of the solution. So there's actually a vocabulary word. Standardized solution means that you know its concentration. So if I asked you to make a standardized solution, I would need to tell you what concentration you're trying to make. Once you are really careful about how you make that, which we're going to go through today, then you know the concentration of your solution. So what tool is used to make a solution? It's actually a very special type of glassware known as a volumetric flask. We have some really big ones. This one actually makes a whole liter of solution. And then we have some smaller ones that we're going to use today, 250 milliliters and 100 milliliters, and there are some other sizes. The idea with a volumetric flask is it makes exactly one volume. The design of a volumetric flask is specifically geared towards making solutions. You want to make sure that you're using the glassware correctly, so I want to go over what the parts of the volumetric flask are and why you would want to use each part for its purpose. So let's start at the bottom. You're going to put solid particles in here, and then you're going to try to mix them in with water, which means that we're going to be dealing with dissolution. We want to make sure that those particles dissolve in the water. So this big wide bottom is perfect for mixing. Remember, we want agitation. So we're going to want to be mixing up the salt particles, or solute particles, I should say. We're going to use salt as an example today. Mixing that up with water and getting that to dissolve. So that's why this has this big basin, huge big basin, good for lots of agitation or swashing around of the water. Then we're going to want to be real careful about measuring the final volume, which is why these are only designed to measure one volume. The one volume is going to be marked with something called an etch mark. It is literally etched into the glass. That marking is the one marking that tells you you have the set volume. There's no way to fill it halfway and find, like, this is a 1 liter, so I can't fill it halfway and get 500 milliliters. I have no guidance for that. I have no way to determine an in-between volume. Unlike with a graduated cylinder, which can find multiple different volumes. This is what you get when you have a uniform width throughout. This is designed specifically for one volume, and so there is no way to use it for other volumes. So that's our etch mark. And then the skinny neck is going to allow for more precision. Whenever you take that measurement, the skinnier the neck, the more precise your measurements can be, or the more decimal places you can give your answer. When we're making these solutions, the volumes that we're going to discuss are total volumes of solution. There is not a way to tell the volume of the solute versus the volume of the solvent. That is why those bottom flasks are designed to hold both. So another point of the etch mark here, it points out that the volumes are not additive, meaning you cannot take the volume of solute and the volume of solvent, add them together and get the volume of solution. You could do that with mass, since masses are set, the amount of matter in a substance is pretty set, but the volumes are not additive. So let me use an example to explain why. Picture a bag of basketballs. Say it takes up a set amount of space. Now take a separate bag, about the same size, and fill it full of golf balls. So if I added the volumes, I would get a large volume. But if I took the golf balls and poured it in the bag of basketballs, those golf balls would settle in between the spacing of the basketballs, meaning the bag of mixed balls would take up less space than the separate bags would take up. The same thing is going to happen with your particles. Small particles will fit in between the spacing of the large particles, and there is no reason we even need to separate out what's the volume of the water versus what's the volume of the solute. All that matters is the total volume of solution, because we're trying to make something of set molarity, which is set as a ratio per solution, moles per solution. So the etch mark is going to be perfect for that, because it's going to measure the volume of total solution. We're going to put our solute in first, then we're going to add our solvent, and it's all going to be there when we take our volume reading at the etch mark. So every single piece of this glassware is designed for a purpose. So that means you always, always, always want to make sure that when you make a solution, you're using a volumetric flask. Never make a solution in a graduated cylinder or a beaker. It's just not known volumes, and so you're not going to get precise concentrations. All right, so let's try making a standardized solution, something where we know the volume, using a 250 milliliter glassware in order to get exactly 250 milliliters of solution. And I want to make sure I set the concentration to 0.3. So I'm going to get rid of all of the volumetric flasks except for the 250 milliliter one. When I do that, I want to now calculate how much solute to put in there. So my molarity equation is going to come into play here. Molarity equals moles of solute per liter of solution. So what is given? First, I have my 250 milliliters, which would be my volume of total solution. So am I going to plug in 250 to the bottom? I can't because it's milliliters. So I have to convert milliliters to liters. 250 milliliters over 1. So I'm going to put milliliters on the bottom and liters on top. And there are 1,000 milliliters in a liter. So you may know this basically means we are moving the decimal place back 3 places to get the liters. So that's what I'll plug in on the bottom. 0.250 liters. The other thing I'm given is the 0.300 molarity. So I'm going to plug that in on the left. The thing I don't know would be on the top. By definition, because I am solving for molarity, moles per liter, what I solve for, X here, will be the moles of solution. So if I take 0.250 and multiply it by 0.3, it's going to give me X. So I'm going to type in my 0.3 times my 0.25, and I get 0.075, but I want to keep the 3 sig figs, and that by definition will be the number of moles. That's great. I've used my formula, but now I go to actually make the solution, and what could I use to measure moles? There's not a device for that. Magic molometer, here I come. Like there's not a thing that I can use to measure moles, but I do have a scale. So could I convert moles to something that I could use a scale with? Grams. So mole on the bottom and gram on top. 1 mole, and then I'm going to use the molar mass of the sodium chloride, which is 58.44. So essentially this means I'm taking my moles and I'm multiplying it times 58.44, and we get 4.38. So that is actually something I can work with. 4.38 grams of solute. So now I'm going to turn on my scale and I'm going to zero it with the weigh boat. Weigh boats are used for measuring substances. They're nice and flexible. I want to make sure it's nice and clean. I'm going to zero the scale with the weigh boat on it. So that way I'm just getting the reading of how much solute I am putting in. So now I'm going to start adding my solute, which in this case I'm just going to use the NaCl or table salt. And I want to try to hit 4.38 exactly. So very slowly, getting really close to 4.38. Okay. As you get close, you may want to use a scapula to add small parts of salt, or if you go over, you may want to use a scapula to remove some. You want to make sure that you get to this level of precision, exactly 4.38. When you're making a standardized solution, the details matter. So I've got now exactly 4.38 grams of salt. Now that's my solute that I'm going to add into my volumetric flask. So let me kind of change the coloring here so you can see what's going on. I've got my salt. I'm going to bend the weigh boat, bending the weigh boat so that I can use it almost like a funnel in order to add the NaCl to the flask. It's nice and slow. You want to make sure every bit of particle makes it inside of the flask. But if the flask is the least bit damp, some of the particles will stick to the glass in the neck. So you're going to want to use some kind of dropper bottle so you can kind of put the water along the sides in order to wash all of the particulate down. Before you start adding a lot of water, you want to make sure that all of the salt is down in that bottom bulb of the volumetric flask. We want to make sure it dissolves. Once it's all down in there, you're going to have a pretty cloudy solution. So this indicates that the salt particles haven't really completely dissolved into the water yet. It's probably a solubility issue. We probably have too much salt particle per water. So the next thing that I want to do is add some more water, trying to get this to dissolve. But the problem is I want to make sure that I can still agitate it in order to get it to go into solution. Remember, agitation increases the rate of dissolution. So I'm going to add this in stages. To start with, I'm only going to put water about 1/3 of the way up the bulb. Then I'm going to shake it. Then I'm going to add some more water, shake it again, and then show you how to finish that off. So as I'm adding water to the bulb, I don't need something as precise as the water bottle. I'm just going to use a beaker of our water. By the way, we're always using something called DI water so that we have a nice pure solution. All right, once I've got that about 1/3 of the way filled, I'm going to start agitating or shaking, stirring up my solution. Another trick you might use to increase the rate of dissolution is to increase the temperature. So you could maybe put this on a hot plate. You could even use a stir bar with the hot plate, and that way you're increasing both the heat available and the chaos in the solution, trying to get this salt to dissolve. So once it's mostly clear, I want to go ahead and add another 1/3, so filling this up about 2/3 of the way total. Again, more water is going to allow more to dissolve, right? But you want to make sure that you still have room for agitation. All right, so mixing this up even more. And the idea in this third part is that we can get it completely dissolved. If we add much more water, I'm not going to get very much motion of this water as I shake. So I want more agitation. I need that room. So we're going to shake this as long as it takes, or heat it as long as it takes, to get that solute into solution. Once it's all dissolved and I have a crystal clear solution, then I can add the rest of my water. But I want to be really careful of the etch mark. So as long as I'm in the bulb, I can still keep using my beaker of DI water. Just make sure I do it pretty slowly, getting kind of close to the neck, the skinny neck. Don't want to be too impatient, because once you get to the skinny neck, it goes really fast. So now I'm going to switch over to something that can dispense water at a slower rate, much more drop-wise. So maybe a pipette or a wash bottle like this. And I want to get eye level and try to watch the etch mark and fill it so that the bottom of the meniscus is touching the etch mark. So it's a difference of a drop or two. And the goal here is that the actual bottom of the meniscus is in line with the etch mark. This is going to show that we have exactly made 250 milliliters of solution. That volume includes not only the volume of the water, but also the volume of the salt. So our volumetric flask measures the total volume of solution. We made sure that the scale got the exact amount of solute, and that means that I now have a perfectly standardized solution, because I know both the amount of solute and the amount of total solution is correct. So, first thing we did was add the correct amount of solute, and then the second thing we did is make sure that we hit the volume precisely. Biggest mistake I hear with people describing how to do this is saying that we would add 250 milliliters of water. This is a total 250 milliliters, and we put the salt in first. So that's going to then be a total volume of solution, not 250 milliliters of water. That would be too much water. That 250 is supposed to include the salt too. All right, so that is making something from a stock reagent, like on stock, on a shelf, in stock, pulling this solid NaCl. So basically it means making it from a solid and using that in order to make the solution. There is another way that we can make solutions of known concentration, and that's through a process called dilution. So typically, an aqueous compound would come concentrated, meaning they're going to pack as much particle into that as they sell it as possible. So typically, a standard solution concentration, if you're going to buy it like from Flynn or something, would be about 12 molar. So I would order 12 molar hydrochloric acid, and then for each lab that I did, I would take that 12 molar hydrochloric acid and dilute it down to a less concentrated version, maybe 3 molar, maybe 1 molar, maybe 0.1 molar. The idea is I can change the concentration. So how do you dilute or decrease the concentration of a solution? Think about the particles. In a concentrated solution, the particles of solute would be very close together because there's a lot of them per volume. In a dilute solution, those particles would spread out more, meaning they need to be further apart. Well, what would we need to add in order to make them further apart? Some more solvent, or usually some more water. So to go from concentrated to dilute, we need more water. But if we're going to keep this standardized, we need to make sure that we're very precise about the volumes we're using for both the concentrated solution and the water. So there is a formula for this. The dilution equation is M1V1 equals M2V2. The idea here is that one side would represent the concentrated solution, whereas the other side would represent the dilute solution. So typically a problem will tell you the concentration you're starting with and the concentration you want to dilute to. And then they'll typically tell you how much of that final solution you want to make. So what you're solving for here is the volume of concentrated solution needed to basically act as the solute in the dilute solution. What you are not directly solving for is the amount of water. But that's okay, because we have the volumetric flask. So we know that we're just going to add water to the etch mark. All right, so let's try one. Oops. There we go. So we're going to take the 0.3 molar sodium chloride. You may recognize that that's exactly what we just made here. So when it comes time to doing the solution, I'm literally going to dilute the same solution that we just made. So I'm going to take my M1V1 equals M2V2. Again, letting this part be the concentrated and this part be dilute. Okay, so do I have the concentration of the concentrated solution? The concentrated solution would be the one with a higher molarity. So that would be the 0.300. And you're never going to know the volume of that guy. Yes, I know I made 250 milliliters of solution, but would it make sense that I would use all 250 milliliters of solution to make only 100 milliliters of something that has more water added to it? We're not using the 250. We need to find out how much of that 250 to use. All right, so then the molarity of the dilute or less concentrated solution is our 0.1. And then the total volume we're trying to make in the end is 100 milliliters of that 0.1. So you basically want to be careful that you are pairing things correctly. The volume of the dilute solution go together, and then the concentrated solution, we're never going to know its volume. That's always what we're looking for. So now to solve for V1, we're going to divide by this 0.300 molality. Isolating V1 on the left, molarity will cancel out, leaving milliliters as my unit for volume, which is okay. Often here I get asked, well, weren't we supposed to be in liters? Well, yes, if you're using molarity equals moles over liters. We're not using that exact formula, so we don't have to abide by those exact rules. It's fine if you want to convert it to liters, but most of your volumetric flasks are labeled in milliliters, so I'm going to go ahead and leave it in milliliters. So now the question is, what is 0.1 times 100 divided by our 0.3? What is our total volume? And that's going to be 33.3 using the 3 significant figures. So we want to figure out what to do with that volume. What does that volume tell us? Using a little bit of common sense when we actually go and we look at our materials. So I have my concentrated solution. I have my 0.3 molar solution. I know I'm trying to make 100 milliliters of dilute solution, which means I should make that dilute solution in this 100 milliliter flask. The question is, how much of the concentrated solution do I put in this flask? And that is what we solved for. We did not and will not solve for the amount of water to add. This is the amount of concentrated solution. Look at what it's next to in the formula. So I want to use a graduated cylinder to measure out the 33.3 milliliters. So we want to do that very precisely, making sure you use all the right skills to use the graduated cylinder. Meaning when it's time to measure, you're getting down to eye level and you're getting the meniscus even with the number we are aiming for, the 33.3. Once we have that measured out exactly, we are ready to transfer it to the volumetric flask. Sometimes students try to make solution in the graduated cylinder. Volumetric flasks were designed to make solutions, so take advantage of them. Do not make your solution in the graduated cylinder. Transfer the concentrated solution to the 100 milliliter volumetric flask. Now we want to know how much more water. And the answer is just follow the etch mark. I just want to know, or I just want to do enough water to reach that etch mark. Notice that this time, because we already had a solution, it's already dissolved. So the only stages that I really need for this is to be careful when I get to the neck. I can use a beaker to fill up to the neck, but then I want to switch over to something more precise to make sure I hit that etch mark. But agitation isn't a problem here because we already have everything dissolved. So next I'm going to use my beaker to get pretty close to the neck. Again, patience, patience. We don't want to overshoot it. Now that I'm kind of at my neck, water level about here and etch mark right about there. So we want to close that gap using something more precise, like the wash bottle or a pipette. And we're going to fill that so that the bottom of the meniscus touches the etch mark. So now I have the water level exactly even to the etch mark. What do you think we should do if I accidentally overshot it? It happens all the time. Just a little bit past the etch mark. Could I just dump that out real quick and get back down to the etch mark? Maybe go back and forth, dump it out, fill some more water back and forth? Well, no, because everything you dump out would have salt particles in it. We very deliberately measured how much salt we put into the original solution, and we very deliberately measured how much of that concentrated solution we transferred into this flask. So if you start dumping stuff out of here, you're going to be losing those particles, meaning the concentration wouldn't be what you're saying it is. You have to have the exact amount of solute when you have a standardized solution. So by precisely measuring in the first place, and then precisely watching our volumes, we can make sure that we always have standardized solutions, or solutions of known concentration. Whether that's preparing it from a stock reagent, or the solid, or diluting that from a concentrated solution. If we're careful about our measurements, we're going to make sure that we know the concentrations. All right. So the dilution formula we see here in just a minute. Dilution formula in order to solve for the volume. But the tricky part is what this volume actually represents. So this is always the volume of the concentrated solution. So we're going to measure out that amount of concentrated solution into the correct volumetric flask and then just fill the water to the etch mark. It may seem that if I have 33 milliliters of concentrated solution and I'm aiming for 100 total, that would be about 66, 67 milliliters of water. But if you did that, it would actually be short of the etch mark because the salt particles have a huge molar mass of 58, the water particles have a small molar mass of 18, and so those particles are going to settle in between each other. So you're actually going to be using more than 66, 67 milliliters of water. You want to make sure that you're using the volumetric flask with a very precise skinny neck to measure exactly how much total solution that you have. So that's going to take care of all of our concentration calculations now. We've done several to start with, from mass percent and molality. Then we really focused on molarity and how to use those equations to actually physically make solutions. Physically making solutions is one of the most important skills you could have as a chemist. So that's going to wrap up Notes B. Our next set of notes will be Note C for Unit 8, which will be all about colligative properties. See you there.